Hello guys, welcome to Vsquare. In this video, we are going to concentrate on formulation of the Lagrangian for a free particle. In the previous video, we had defined something known as an inertial frame of reference with respect to which space and time are homogeneous and space is isotropic. Now we saw in the previous video that because of this, the consequence is that the Lagrangian doesn't depend for a free particle. Lagrangian for a free particle, okay, doesn't depend on the position vector or the time t. Okay, it should be and. All right, and this particular fact that space is isotropic with respect to an inertial frame makes sure that the Lagrangian is not dependent on the direction of the velocity. So since Lagrangian is dependent on the position, velocity and time, and since it's not dependent on position and time because of the homogeneous property of space and time, it must depend only on the velocity, and I'm only talking about free particle here. And since isotropic, this should be C. So since space is isotropic, it implies that there is no special direction, or in other words, the free particle behaves the same way in any direction of your choice, and therefore it should not depend on the direction of velocity also, which implies L depends only on magnitude of V. And how do we get the magnitude of V? There are many ways. So for example, to define magnitude, we can define it as mod V, or we can define it as V dot V, which gives V square, where V is equal to magnitude of V. And we can also use V power 4 or any even power for that matter, and all of them will give some information regarding the magnitude of the velocity. But in the previous video, we had assumed that L is only a function of V square, and I said that further justification for this will be given in this video. Alright, so let's first of all, if you go back to our second or third lecture, we had assumed that L is a twice differentiable function, alright, with respect to R, V as well as T, and that implies, so L is twice differentiable, okay, with respect to V by definition, okay, and that means we cannot have L as a function of mod V, because mod V is not differentiable at 0, okay, so it cannot be this. So now all we are left with is even powers of V, and to know which one is correct, we have to go back to our Galileos transformations, okay. So Galileos transformations, what do they say? They simply say that if I have a position vector r dash with respect to a frame of reference k dash, then in terms of the position vector of the original frame of reference, it will be given by this transformation, okay. And we had seen in the previous video that under these transformations, so under these transformations. Okay, in other words, under any inertial frame, the laws of mechanics are the same. So laws of mechanics remain the same. And this implies form of the Lagrangian must be same or equivalent, or in other words, L dash must be equivalent to L. Okay. And on our lecture about the Lagrangian, we had seen that L dash defined by some constant A multiplied by L plus some constant B plus some total derivative of a function which depends only on the position and time. Such a L dash in terms of the old L, if we define it in this way, then we had seen that this implies L dash and L are equivalent. By equivalent, what we mean is that if we apply the Euler-Lagrange condition to both of these Lagrangians, that is L dash and L, we are going to end up with the same conditions or the same set of equations. Okay. The only difference will be the overall multiplication by the constant A. Alright. So what does this mean? So if we consider, so first let's consider L to be a function of V square. Okay, we'll see what happens to higher even powers, but first let's see what happens to V square. Okay, then if you consider, so let's consider, so this is with respect to K, which is an inertial frame. Okay, now let's consider K dash, which is another inertial frame which is moving with V with respect to K. Okay, then the transformation, Galileos transformation, tells us that the new free particle velocity will be the old velocity plus the velocity of the K dash frame of reference. All right. Okay. Then if we, so this means L can be written as A V square plus B. Okay. We can also consider d by dt of f of RT, but it is not going to make any difference and it will just make the math complicated. You can try to work that on your own. But if we consider this, then L dash would be simply A times V dash square plus B. Okay. And what will this V dash be? So V dash square is nothing but V dash dot V dash. This is nothing but, this should be a vector, V plus V dot V plus V. This will give us V square plus 2 times V dot V plus V square. Alright. So this means, so that means that, let's go over here, L dash will be A times, we know that it's A times V dash square plus B. So this will be A times V square plus 2 V dot V plus V square plus B. And this will be A V square and I'm going to take this b back here, plus b plus a times 2 into, okay, 2 into v. Now this v can be written as, so v is equal to dr by dt, okay. So I can write this as, and v is a constant, okay. So v is a constant, which implies dv by dt is 0, okay. So I can write v dot v as d by dt times r dot v, which is nothing but d by dt times r dot v plus r dot dv by dt. This goes to 0, so this is equal to this. So I can write it here as d by dt of r dot v plus, I can write this, the next term, as d by dt of v square t, okay. So this means I'm having L dash as equal to ab square plus b plus d by dt of 2a times r dot v plus v squared times t, okay. So I can consider this as a function of r and t, and we had already seen that if L dash differs from L by a total derivative of a function which depends on just the position, coordinate and time, then the two Lagrangians are equivalent, and therefore L dash and L are equivalent, okay, when L is equal to av square plus b. Alright. And if we had added another function d by dt of g of t, it will simply come as another term. So if this was d by dt g of rt, then this would simply turn out to be plus d by dt g of rt here, and we will simply get it as d by dt of f plus g, okay. So nothing changes there. So when we do a Galilean transformation, we should expect that the laws of motion should remain unchanged, which in turn implies that the form of the Lagrangian should not change, or in other words, the two Lagrangians with respect to the two different frame of references must remain equivalent, okay. And this happens when we consider L as a function of v square. Now let's see what will happen if you consider L as a function of v power 4, for example, or any higher power, okay. So now let's consider L as a function of v power 4, let's say, okay. Then L dash with respect to reference k dash is going to be a v dash power 4 plus b, which is a into v plus v to the power 4 plus b, okay. So this is a dot product. Then if you expand this, okay, so this is nothing but v plus v dot v plus v into v plus v dot v plus v. Okay, if you expand this term, you are going to get some v power 4, okay, plus you are also going to get terms of the form which have v square term, right, plus v square into v square, such forms of terms. You will get v dot v the whole square terms. Okay, obviously they will have some coefficient here, but if you observe, and plus some other terms. Okay, and if you expand and observe that this has terms of this kind, okay, which is basically dr by dt the whole square. Okay, and because of this, it's not possible to express L dash as L plus some total derivative of a function which depends only on position and time. Why? Because it has a term of this form, and because of that we cannot get this, and as a consequence, so this implies L dash and L will not be equivalent. Okay, but this is against the Galileo's relativity principle, which says that laws of mechanics must be the same in any inertial frame of reference, which is violated if we consider L to be dependent on v power 4. Okay, so this works, that is L dash and L to be equivalent will work only if L is a function of v square alone. Okay, so that is the justification for why L must be a function of v square. Alright, now let us now, so we said that L is some function av square plus b plus some, you can always say d by dt of some g r of t, because any Lagrangian which is defined in this form will define a free particle when you apply the Euler-Lagrange equation. Alright, but now let's so we can choose any Lagrangian of this form, and the Euler-Lagrange equations say that what does the Euler-Lagrange equation say? It says dou L by dou R minus d by dt of dou L by dou V should be equal to 0. Okay, let's compare this to, so this is same as saying d by dt of dou L by dou V equal to dou L by dou R, right? Okay, so this is similar to, if you compare, so this should give us equations of motion, right? Okay, and for a free particle, we know that mass times the acceleration must be 0. Okay, or in other words, we can say that d by dt of the momentum must be 0. Okay, now since L doesn't depend on r, this term is going to be 0. Okay, and let's compare this. So d by dt of dou L by dou V must be 0. Okay. Then if you write L as a v square plus b plus d by dt of g of r and t, then dou L by dou V will make sure this goes to 0 and this goes to 0, and we will get this as d by dt of 2av equal to 0. Right? Now let's compare this equation and this equation. So comparing this, we get, okay, so this will be the vector v. So we get d by dt, this p is defined as mass times the velocity. So d by dt mv must be equal to d by dt 2av. Right? Okay. So this implies a should be equal to m by 2. Therefore, the Lagrangian is half mv square plus b plus d by dt times g of rt. Okay. Now, since any Lagrangian which is of this form, are equivalent when I add it with some constant and the total derivative of a function, then I can define my L free as L minus b minus d by dt g of rt, because both of them is going to give the same equations of motion. So this gives L free is equal to half mv square. Okay. So if we consider that the Lagrangian for a free particle is just half mv square, it is going to make our calculations easier, because true, we can consider it to be having this form, but it is just going to make our calculations more messy, and since this and this are both mechanically equivalent, that is, they end up giving the same equations of motion, we can always consider this to be our Lagrangian for the free particle. Okay. So therefore, Lagrangian for a free particle is just half mv square. Okay, where m is the mass. All right. Now, if you consider, so let's consider, let's consider two non-interacting free particles. Okay. Individually, their Lagrangians can be defined as half m1 v1 square and half m2 v2 square. Okay, and I can always define, okay, my Lagrangian to be, so I can always say L dash as some half m1 c1 v1 square plus d1 plus d by dt of some function, because I will still get the same result if I consider them individually. But what happens if I consider the two non-interacting particle itself as an entire system? Okay, so if we consider 1 plus 2 as a system, that is, we consider both the particles together as a system, then L system, as we saw in our previous lectures, will be given by L1 plus L2. Okay, now this is nothing but half m1 v1 square plus half m2 v2 square. What should this give us? So this L system, when we apply Euler-Lagrange's equation to this L system, we should get the behavior or the mechanical behavior of the entire system, or in other words, we should get how the individual particles are going to move, okay, or how they are going to behave mechanically. So this should give how both particles are going to move. Okay, now you may ask the question, can this happen? Okay, can we have L system dash as some half m1 c1 v1 square, where c1 is a constant, and half m2 c2 v2 square? Okay, can this happen? And the answer is, because individually the Lagrangians can be multiplied by any constant, and it is not going to give me any different set of equations which describe the motion of the particles when I consider them individually. But when I consider them together as a whole, I will not be able to do this, because this will be the equations which you get from this. Okay, so if we solve this, the Euler-Lagrange equation for this, what are you going to get? We'll get d by dt dou L dash cis by dou V. Okay, we have to actually we'll get two sets of equations, so that is V1 equal to 0 and d by dt dou L dash cis by dou V2 equal to 0, and applying this individually, what are we going to get? We are going to get m1 c1 v1, so d by dt of this is equal to 0, and d by dt of m1 c2 v2 equal to 0. Okay, so what does this tell us? Of course, it tells us that the individual particles are moving freely. Okay, in this case it will work, but if you consider the particles to be experiencing some sort of a force, then for the same force, if the two particles have different masses, they are going to respond differently. Okay, so the ratio of the masses is going to matter when you consider forces. Okay, therefore when you consider forces, the ratio of the masses is going to matter. So this implies that we cannot simply arbitrarily choose any constant C1 and C2 to get the Lagrangian for the entire system. We have to be more careful, okay, because we have to preserve the ratio of the masses to properly describe what is happening, okay, especially when there are interacting forces. Okay, in this case it turns out that you can get away by multiplying two different constants, but physically when you think about it, we need to make sure that the Lagrangians are also going to capture the ratio of the masses of the two particles. And this is especially important when the particles are experiencing some kind of forces. Okay, so this implies that we can't arbitrarily choose C1 and C2. Okay, so how do we choose the constants then? We can only have C1 equal to C2, okay, because only then the ratio of the masses are going to remain the same. So if here C1 and C2 were the same, then L1 dash by L2 dash is going to be constant, okay, or the ratio is going to remain the same only if C1 and C2 are the same. Okay, so that is something that should be noted, and it's something that's important to know, and which means that we cannot simply arbitrarily multiply the individual Lagrangians when we consider two or more particles as a system or as a whole system. Then we need to preserve the ratio of the masses in order to extract how they are going to react to different forces. Okay, so we are going to understand this particular statement better as we move forward, but for now just believe me that the ratios of the masses needs to be conserved, and therefore we cannot simply multiply any two different constants to the individual Lagrangians and say that L dash system is still going to be equivalent. Okay, so that's it for this video. So to summarize, we basically justified why the Lagrangian for a free particle must be a function of V square and not say mod V or V power 4 or any even power of V. And we also made a note saying that if you consider two or more particles, then if you consider the Lagrangian of the entire system, the masses needs to be conserved, and therefore we cannot simply arbitrarily multiply any constants to the individual Lagrangians to get the Lagrangian of the entire system. Okay, we can multiply by a constant which is common for all the Lagrangians. That will be correct because the ratio of the masses are still going to be the same. Okay, so thank you for watching, and I will see you in the next video.